What do Richard Branson and Los Alamos National Laboratory have in common? Well, until late this summer, probably not much. But in mid-August, for the first time, the lab partnered with a private company to launch a rocket into space that carried a Los Alamos-designed communications payload. The payload was itself a first, and we'll get into that later. But to launch the rocket for the first time, Los Alamos partnered with New Mexico's Spaceport America, which is, you guessed it, the same place where Richard Branson launched to space this summer. In this episode of the podcast, we're taking you behind the scenes of a rocket launch called a flight test. This mission was part of the Stockpile Responsiveness Program, a law that tasked the lab with developing new ideas on how to quicken the pace for developing technology that will update the nation's nuclear stockpile. To test new ideas and technology, engineers must conduct flight tests, rocket launches that demonstrate these updates will work in real-life scenarios. So they do flight tests. But in the past, these tests were costly and they took years to plan. So a team of lab engineers and scientists came up with a novel approach. Why not use private launch companies to help? From Los Alamos National Laboratory, where better science equals better national security, I'm your host, Brenda Fleming. Join us as National Security Science magazine writer Weston Phippen takes us to the desert of New Mexico, where a dedicated group of lab scientists and engineers put this new approach to the test.
It was afternoon, the day before the launch, and a team of lab engineers and scientists were gathered around a chain-link fence in the desert. Behind the chain-link fence was a large metal garage on wheels. It was a 40-minute drive here from Truth or Consequences, New Mexico, on a winding highway over a dirt road and past the glassy Modern Spaceport America headquarters. To the east, just beyond the mountains, was White Sands Missile Range, the largest military installation in the United States. In a first, the lab had partnered with a private rocket launch company to conduct a flight test. This company was Up Aerospace, a family-run business based in Colorado that had designed, assembled, and would launch the rocket. Standing in front of the fence was Jerry Larson, the company's president, who gave everyone an introduction to himself and what to expect tomorrow.
Well, I worked at Lockheed Martin for 20 years, and I launched rockets at Lockheed Martin, and an opportunity for me to start this company 15 years ago came along. It was really hard to leave Lockheed Martin. I loved my job there. We did amazing things. I took a chance. First 5 years was hard, but the last 10 years we've been able to keep a good business we've launched for Lockheed Martin and Moog and the Air Force and now Los Alamos and a lot of payloads for NASA as well. So it's been a fun ride. We've been very blessed that we've been able to do this. So
behind Larson, a truck slowly pulled away the garage that covered the rocket.
So with that, the big reveal. This is where you ooh and ah. You have a role in this.
For the Los Alamos flight test, named REDX-1, which is short for Responsive Development Experiment, Larson's Up Aerospace used its Space Loft rocket, which weighs 800 pounds and can fly 60 miles into the atmosphere, reaching Mach 6 in 12 seconds. It all sounded relatively straightforward. The rocket would launch tomorrow morning from this relatively small concrete pad. Meanwhile, a satellite in low Earth orbit would pass over the horizon. On its way 60 miles above Earth to the edge of space, the rocket would relay to the satellite important information about the flight. The satellite would then pass that data to ground monitoring stations where lab scientists could examine it in detail. Easy enough, right? Well, not exactly. As Matt Tucker, a program manager with the lab's Office of National Security and International Studies, explained.
Targeting at least an order of magnitude cost compared to what you can do today. And a big part of that is sending the telemetry and flight data up to satellites, which is what this experiment's going to, that's the concept this is going to test. And it's more complicated than it might seem. You have Doppler shift effects because you have two moving bodies, and there's lots of details to figure out. The interesting thing on this one is the satellite we're going to talk to was designed, built by Los Alamos and put into orbit, as part of another Los Alamos program.
But why do all of this in the first place? The weapons in the U.S. nuclear stockpile were designed and built in the 1960s, 70s, and 80s. These weapons remain safe and reliable, largely because of various updates over the years by Los Alamos and other national laboratories. This general maintenance of nuclear weapons is called the Stockpile Stewardship Program, which began 2.5 decades ago. Then, in 2016, the National Nuclear Security Administration created a parallel program called the Stockpile Responsiveness Program. The aim of this program was to engage the, quote, technical capabilities required for all stages of the design, testing, and production of nuclear weapons, as well as working in concert with the Department of Defense to recruit, train, and retain the next generation of weapon designers and engineers. So the lab was tasked, more or less, with 3 main goals. First, to find a way to significantly decrease the time it took to go from concept to prototype when developing updates to the nation's nuclear deterrent. Second, to develop the technology needed to do this. And lastly, to pass this knowledge on to a new generation. So what does stockpile responsiveness have to do with rockets? New technical capabilities for the stockpile require testing, specifically flight testing. A rocket launch can produce environments relevant to those a system would need to survive on an intercontinental ballistic missile launch. In other words, flight tests help ensure systems will perform as expected on the real thing. But when coming up with ways to quicken the pace of development, the Los Alamos team quickly recognized a major hurdle. In the past, flight tests were conducted over the Pacific Ocean and required very specific telemetry data to meet DoD test requirements. This meant relying on a large contingent of DoD assets, like U.S. Navy ships and ground monitoring stations, that supported each test. Lots of people, resources, and vessels were needed for each test to aid with everything from data collection to tracing the impact location and even for recovering the rockets. Given all of this, these experiments were very expensive, roughly $100 million per flight. This limited the lab's ability to test new ideas or to provide the training required for teams to take a system from concept to reality. So a year ago, while discussing solutions, the Red X-1 team came up with a novel idea. From SpaceX and Virgin Galactic to the dozens of smaller companies, private industry is doing what was once reserved for governments, launching rockets. As the Los Alamos team began to discuss this possibility of a private partnership, they realized that it was not only totally doable, but also faster to coordinate and significantly less expensive. That's how the lab found Up Aerospace. The company handled the design and assembly of the rocket, and they even coordinated with all involved parties, including Spaceport America and the Federal Aviation Administration. That left the lab to do what it does best, engineering and designing new technology. By moving flight tests to Spaceport America and relying on the nearby White Sands Missile Range to track the rocket, Los Alamos could cut the time to coordinate a launch by years. It would also save hundreds of millions of dollars. But that left one essential piece missing. Before, the DoD used its resources to receive crucial flight data from the rocket. Information like high or low temperatures, varying accelerations, velocities, and the pressures the rocket experienced. But now, without the DoD's vast resources, the Red X-1 team needed to find a way to send and receive this data on its own. This was the communications payload that the rocket would carry into space, eject, and that would fall back down to the Earth into White Sands missile range. It had taken a year of development, testing, and retesting at the lab to get this payload right. Tomorrow, the Red X-1 team would find out if it would work. The following day, the weather on the morning of August 11th, 2021 was sunny and warm, with a slight but steady wind. The Red X-1 team had returned to the launch site, and many lab employees had brought their families to witness the historic day. While some children tossed a ball back and forth, a group of men and women had gathered around a small folding table. Spaceport America is owned and operated by the state of New Mexico, so several state legislatures had also arrived. Beside the small picnic table was Steve Judd, the lab's stockpile responsiveness program manager. As he spoke, he held an example of the Red X-1 payload in his hand.
The satellite's going to be passing overhead, and then the rocket's going to go up. This is going to eject off, and it's going to start transmitting data. And we want to, see, can we use small, simple satellites that are now everywhere on orbit to talk to a relatively simple communication system and use that to do telemetry. Because if we can prove that out, then we can use this on all of our future launches. So this is taking data on the vehicle. It has temperature sensors, it has accelerometers, it has a gyro on it. So how's it spinning? How's it flying? Is it getting too hot? Is it behaving the way we predicted it should behave? And so
Designing the Red X-1 payload combined several groups at the lab. Up Aerospace had given the team a certain amount of payload space in the rocket to work with, a compartment about 12 inches high and 10 inches wide. The communications system needed to include an antenna, diagnostic equipment, a power source, and other electronics. So once the Red X-1 team figured out how to fit everything inside a conical-shaped payload, they now had to worry about what happened when the rocket ejected the payload at 60 miles above Earth. Falling from that far, that fast, meant the payload would endure extreme temperatures, so the lab's Materials Science and Technology Division designed a special silicone-based heat shield able to withstand temperatures of thousands of degrees Fahrenheit. One of the last problems the team had to solve was how to make the payload fall back to Earth and land in a very precise location. A spinning, uncontrollable object hurling 60 miles toward Earth could land anywhere, so the team turned to tungsten, a 17-pound cube of the element, no larger than a coffee cup, was milled to fit at the top of the payload and would act as a ballast to force the payload to fall nose down. After that, the Red X-1 team spent months and months testing the communications payload to ensure it would work in the harsh environment of being blasted to space and falling back to the desert.
RSO-LC, the launch crew has successfully completed the pre-launch procedures. Request permission to proceed with terminal countdown operations. Permission granted. Copy, check 34. Launch crew, we're going to pick up the count at terminal countdown procedures at T-minus 35 minutes. That's in approximately 30 minutes from now.
With the signal that launch time neared, the group dispersed from the folding table near a bank of bleachers where everyone waited for the final countdown. The crowd chatted as 30 minutes turned to 20, then 10, and finally as the announcement arrived.
30 seconds on my mark. 3, 2, 1, mark. T-minus 30 seconds. Vehicle is armed. 20 seconds. For terminal count, T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. Missile away.
As everyone cheered the launch, NSS caught up with Matt Tucker, the program manager with the lab's Office of National Security and International Studies.
Pretty cool, huh? Yeah, that was pretty awesome. Looks like everything went as expected, right on time. So, yeah, no, it's cool seeing the kids run around and stuff. It's so it goes up, and then it goes up. We're listening. Sounds like separations went as expected. So yeah, it should be on its kind of long, slow path back down. About 15 seconds of powered flight and 15 minutes of coming down. At least parts of it nice and smoothly. So yeah. Good day.
Tucker walked quickly back to the plastic folding table where a laptop was now placed. On the screen were two columns. Suddenly, the right-hand column began to fill with text and numbers.
Separation of ZX confirmed. Good flight.
All right, so our payload came out. Everything's looking good. Looks good? Yep. Awesome. Writing data. All right, writing data. All right. Successful experiment.
This was confirmation that the Red X-1 payload had communicated with the satellite and that the satellite was now relaying this information to the ground. But there was one more important element to the day's test. Remember, the Stockpile Responsiveness Program had 3 main objectives for the lab. The Red X-1 team had improved the pace for conducting test flights by partnering with Spaceport America, White Sands Missile Range, and Up Aerospace. It had developed the communications payload to make this possible. But the third aspect was to teach a new generation how to conduct these flight tests. One of those people from this new generation of scientists and engineers had been kept busy during the day's launch. Mechanical engineer James McGlown had spent the day in the Mission Control Office, where he helped to ensure the rocket's ascent and descent were being properly tracked. At 35 years old, McGlown was among the youngest engineers on the team. He'd come to Los Alamos in 2015. Typically, McGlown engineered the small satellites, called CubeSats, for the lab's Agile Space program. This background made him a natural fit for the Red X-1 test because it involves developing small communication devices that typically share a ride on a rocket into space. At first, he'd helped design the internal configuration of the Red X-1 payload, but he was soon brought on in a larger role as a team leader. It had been his job then to oversee that each task on the project was finished on time. He also oversaw the testing of all components individually, then as a whole. On the day of the launch, as he walked out of the Mission Control Office, McGlown was smiling. NSS caught up with him, briefly, just before he walked down the road to a Black Hawk helicopter that was readying to fly members of the team into White Sands Missile Range, where they'd recover the payload.
What were you doing today in the skiff-looking thing? So today I was coordinating all of the support teams. So we had a ground station at the Alamogordo Airport listening for telemetry on the ground. We had a satellite operator that was commanding the satellite that was passing overhead at the time of launch. That was also listening for the telemetry from the vehicle. And then we had a trajectory reconstruction guy. So that was a aerodynamicist back at Los Alamos waiting to get radar data from White Sands and then use that information to predict where it's going to land. And that's for the recovery effort that we're about to go through right now.
Oh, nice. It's pretty exciting. I mean, to be in the first lab-private partnership of this kind.
That's very exciting. But Up Aero has been amazingly professional and very, very good at what they do. This whole thing went smoothly, and we were, due to the nature of the satellite pass, we had to launch pretty much down to the minute, which is usually difficult for rocket launches, right? and we nailed it down to the second. We got it off the pad right at 8:44.
With the Red X1 test a success, Los Alamos plans to carry out 2 of these flight tests per year for 5 years. The potential cost savings of these tests, compared with how they were once conducted, will be at least hundreds of millions of dollars, probably more. Going forward, these flight tests will become more complicated and technical until researchers are ready for full-scale tests in rockets that more closely simulate an actual missile launch. Down the road, the Black Hawk helicopter lifted off. It soared over the desert and disappeared over the mountains into White Sands Missile Range, where the team searched for the Red X1 communications payload. It took some time, but eventually the payload was found, buried 2 feet underground, but almost completely intact.
Thank you for listening to this episode of the National Security Science Podcast. To read more, check out the Winter 2020 issue of the National Security Science magazine, which is now online at lanl.gov/magazine. That's lanl.gov/magazine.